All right. If you do listen to the recording, it's probably going to be being a noisy patch now as I move the microphone. But all right. Starting off for today, on page 216, problem number 17 in the practice problem section, it very blurry says, a 1,325 kilogram car moving north at 27 meters per second collides with a 2,165 kilogram car moving east at 17 meters per second. They stick together. In what direction and with what speed do they move after the collision? So, this type of problem is a little different than what we had done before, because now we have these two objects that are coming in and then they're sticking together and becoming one object. Okay? Don't scratch your name off the All right, this problem is a little bit different than the problem we did before, because before, the problem that we referred to is called a inelastic collision, where these two objects come in, they bounce off of each other, and then they move off in different directions as two separate objects. The one that makes this problem different is the they stick together parts. And that's what we call a perfectly inelastic collision. So a perfectly inelastic collision is one where we start off with these two objects and they stick together and they become one object in the course of that interaction. We talked about that before. I don't know if you remember on the test that we took on impulse momentum to begin with. There was a problem where we talked about a couple of times where there was a guy with a snowball. He was like ice skating and he threw the snowball, and there was one object at the beginning and two objects at the end. Very similar to that, but this time we're going to start with two objects and become one object, but obviously how we handle it is a little different. Because if we go to our picture, cars, so yeah, we'll make these a little bit smaller. So car here and car here. Okay. So it says, car moving north at 27 meters per second. Oh, sorry. 1,325 kilogram car moving north at 27 meters per second. So we've got this car moving in this direction. It says collides with a 2,165 kilogram car moving east at 17 meters per second. We've got this car going here. And it says they stick together. So eventually we're going to end up with one arrow, right? Okay? We have two objects to begin with, one object to end with. All right? First, just by looking at this picture, if you have a blue car that's moving east like this, and the white car that's moving north like this, what's going to happen if they stick together? What can we kind of safely assume is going to happen in this situation here? How are they going to move off together? Yeah, kind of, in like this direction somehow, some way, right? And it says we want to find out with what speed do they move at, or in what direction, and with what speed do they move after the collision. So we're really looking for this section right here. Okay? Good so far? All right. Let's start off with our initial conditions. Okay? What do we know about the situation beforehand? Okay, so we know initial velocities here, right? And we know initial velocity here, right? What else do we know? We know the masses here, and then we know the mass here. And what can we do with that information? Okay, we can calculate the momentum because, as we discussed before, when we have these interactions in two dimensions, even though in this case we have these two objects sticking together and becoming one object, we still have to conserve momentum on the x-axis, and we still have to conserve momentum on the y-axis. Remember, it's momentum that is conserved in these interactions, not velocity. sometimes we can get away with velocity, but in this case we can't. So the first thing we need to do is we need to take our initial velocity, we need to take our mass, initial velocity, and mass to calculate the initial momentum of these two objects. Go. Anybody got anything for me? Blue. Are we good with these two values? Question there.
Yeah, 35,000.
Oh, sorry.
See how it is. 35,875?
No, 700.
775. Okay. Are we good on red?
Yeah.
What?
Oh, really? Oh, yeah, we are.
Sick. Just calculate from now on.
Wait, what? Wait,
That's all I did. My bad.
I was just saying, it's
Monday.
Monday. Okay,
oh,
so we got this. This is our initial condition. Okay? But, as we discussed in this case here, these two objects, they stick together. So at the end, there's only one object. But we still have to conserve momentum on our two axes. If we look at the purple, right, what do we see about the purple? Is it on the x-axis? Is it on the y-axis? No, so it has components. Components that look like this, and that look like this. That was not straight, right?
Nope.
Very good. Okay?
I think we're over.
It's really hard to tell with these steps. Alright. The blue dotted line, the x component of this final momentum. Because it's on the x-axis, it has to have all of the momentum that was on the x-axis to begin with. If we look at our two initial conditions, one of our initial momentums was on the x-axis. This was the only thing on the x-axis before the collision. So, how big do you think this component of the final momentum has to be? It's got to be exactly the same, because there was only one to begin with there was only one momentum on the x-axis to begin with. And then, taking that same logic, right, this one, right, the white car, it was on the y-axis. Was there anything else on the y-axis before the collision?
no.
There was not. That means that this final momentum, or the y component of this final momentum, right, has to be equal to whatever the momentum on the y-axis was to begin with. Now what do we have? You have a right triangle. And what do you know about said right triangle? You know two of the sides. If you know two of the sides of a right triangle, you should be able to figure out the hypotenuse of that right triangle. Also, you should be able to figure out the direction at which that object moves, because that's important. It asks you for it in the question. Once you figure out the hypotenuse of this right triangle, is that the answer to this question? No, it is not. Because what quantity is conserved in this collision? Momentum is the conserved quantity, but this question is asking you for the speed, or the direction in the speed, which is velocity. This purple after the collision, right? What's the mass of that object after the collision? We said the two things come together and become one object. So the mass of that object has to be the combined mass of those two cars to begin with. Start calculating. This just to decorate here. A squared plus b squared equals c squared. Oh, the angle. Change tangent. Inverse tangent, right?
Like those numbers?
Yep. Because it's the momentum that's conserved.
But how do you do that first?
Yeah, do you
Like it.
Are you in radians for math class? For sure.
So where's PF?
So, listen, PF, the final momentum, is going to be the solid purple arrow. Because that's, remember we said that the dotted ones, they came from the initial momentums of those, on the x-axis and the y-axis. So this is actually the final momentum, is the solid line.
Okay.
So that number, the 51,327, that'll go here, okay? And then like we talked about that, the mass of that object is going to be the combined mass of those two together. Good there? Questions? All right. So that's the first example of a perfectly inelastic collision. All right. I'm going to stop the recording, and then I got one more example to do. I'm going to stop the recording just so it's